Welcome! This video is about homogeneous first-order non-constant coefficients equations, always in the setting of ODEs. So if we look at our terminology, we can easily figure out what we have. It's an order 1, linear, non-constant coefficients. We're looking for non-trivial solutions, and we're at the moment limiting ourselves to the homogeneous case. So in the global setting, first order linear, what we would have is finding a function y such that this equation holds. Y prime plus px y equal qx. We're now in the case of non-constant coefficients, so p and q depend on x. And just to remind you, we're looking for a function y that goes from an interval in R to R. We start with the homogeneous equation, so we're asking qx to be always equal to 0, thus simplifying our initial equation. And we're doing a split of the two parts, and we are writing y prime as dy dx. This is a formalism that called Lagrangian formalism, and it makes sense if you go into the analysis. We're not going to go into that. I just assure you that this is something that mathematically can be done. And we're going to split. We're going to bring the dx on the right part and the y on the left part. Now, if you're familiar with integrals, when you have something depending on x dx, you can change the name of variables. So now we're going to call it t just to make it a bit easier, and we're going to take the integral on both sides, going from 0 to x. The left side is trivial, so we'll have the logarithm of y from 0 to x minus the integral from 0 to x of pt dt. P is given as a data of the problem, so that is not problematic other than the fact that you have to compute that integral. So we're going to put explicitly c as a constant that draws in the logarithm of y at 0. And now that we have that, because we want to solve for y, we want to get rid of the logarithm. So we shift c on the other side, and we exponentiate both sides. Now we have e at the integral of minus pt dt plus a constant. Well, we can drag that e to the c out of it and just put a constant a in front of everything. So this is the solution of the homogeneous problem. As you can see, you can still have some freedom in choosing a if you have a boundary condition or an initial condition. For example, if we had an initial value for, let's say, y0 equal to 1, well, we can fix the value of a explicitly. Let's go into the non-homogeneous case. So as before, we know the order being 1, we want something linear, non-constant coefficients, we're looking for non-trivial solutions, and now we choose for non-homogeneous problems. So we are assuming qx to be different than 0, at least for some values of x. And now I want to bring to you the idea of Ansatz. It's a German word that is like a claim and deduction. We try to guess that y of x is equal to the same thing we got the previous time. So a times the exponential of minus the integral of pt dt. This doesn't take into consideration q at all, so it's clearly a rough approximation. But what we can do is just say, well, what if a was not a constant, but a function of x itself? This is what we call variation of parameters. In the first equation, a was just a fixed parameter. Now it can variate over x. And we want to see if this option for y is a possibility to solve our equation. So we have shifted the question from what is y to what is a of x. The first thing we want to do is try to plug our ansatz for y into the first equation that we have. So we develop what is y prime with our ansatz. This is a function of a and p, So it's a prime e at the minus the integral of pt dt. We're taking the derivative of the first part, and then the derivative of the second part, ax times d over dx of the integral 0 to x pt dt, and the same exponent as before. Now for the fundamental law of calculus, the derivative and the integral over x cancel out. So we have this equation here, and we want to plug it in the first equation. We first simplify it a little bit. The exponential is always the same, so we can take it out of the parentheses. We know y prime, computed depending on our ansatz. We remember our ODE. We plug things in, and you notice that things simplify quite a bit. We have a prime equal a function of x. So we can just integrate on both sides, and by direct integration we have a formula for a. Might not be the most straightforward thing ever, but it's something that solves our problem, because if we plug the value of a inside what we had before, we can solve the non-homogeneous problem, at least formally. What else can we solve by hand? Well, we're going to go through most of the options of things that can be solved by hand, and pretty much everything linear can be solved by hand. Nonlinear problems tend to be extremely hard. As an example of things that can be extremely hard, I want to bring the Navier-Stokes equation. It's a PDE, so we're going to get to that towards the end of this course, but it's also a millennium problem. That means that if you ever get to solve the Navier-Stokes equation in any way or form under some very mild conditions, you would pretty much be the most famous mathematician for the next 100 years.